What if a simple pendulum which is in motion slips midway and its length increases? How would that affect things? Hi, I'm Divya Das. This is For the Love of Physics, and in today's video I want to discuss this very interesting problem in which there is a simple pendulum of some bob having mass m connected to a point of suspension using a massless inextensible string of length L, which is, let's suppose, displaced initially by angle theta and let go. If the pendulum is in motion but midway near the equilibrium point it suddenly slips. Let's suppose the wire that was connecting it to the point of suspension, it was not tied properly, so it slips by a certain distance of del. So how would that change things? So what would be the new angle theta dash that it would be displaced to the other end? So how can we find the relationship between the initial displacement theta and the final displacement on the other end theta dash for this kind of a problem? This is a very interesting problem because it connects different concepts together. Concepts of force, tension, conservation of energy, conservation of angular momentum, as well as work done for non-conservative forces. So let's start with a very simple diagram of what happens to a pendulum which is in motion. The pendulum is initially displaced from position A, where it was at angle theta in the left hand side direction. After traveling midway at location B, let's suppose it slips within a very short interval of time. So the slippage is almost instantaneous. So it goes from B to C instantaneously, and from then on it travels along the path C to D. So essentially the pendulum goes from A, B, C and D. First I want to analyze the motion between A and B. So because the pendulum starts from rest, it has a certain amount of potential energy, but that potential energy gets converted to kinetic energy by the time it reaches the middle. So it has a pure velocity at this particular point B. So if I want to calculate what is the velocity of the pendulum at this particular point B, then I can apply conservation of energy principle, right? At location A, since the pendulum was at rest, it was simply released from location A. It only had potential energy, right? So let's suppose the vertical height that it travels as it goes from A to B is equal to h. So if I consider the lower point to be the reference for potential energy, because potential energy is something that we can calculate based on a reference of our choice. So let's suppose the lowest point is the reference for potential energy. In that situation, initially at location A, the total amount of energy is equal to mgh. Did not have any kinetic energy. But by the time it reaches location B, where it had pure kinetic energy, based on our reference, it had zero potential energy. So this is going to be equal to half m v square. But what is h here? H is simply equal to, because this I am going to call as theta angle. So h is simply equal to L 1 minus cos theta. How? Well, this is L minus this distance, which is L cos theta. So this turns out to be L1 minus cos theta. So if I simplify this expression, I should get velocity square, v square is equal to, it cancel out mm on both sides and you end up getting 2gh, where h is equal to L1 minus cos theta. So this gives us v square upon L, which is equal to 2g1 minus cos theta. Now why have I obtained this expression? Well, it's going to be useful later on. Just keep it in mind. Let's suppose this is point number 1. So the pendulum starts from location A and it travels towards location B. At location B, it had pure kinetic energy with a velocity which is given by this particular expression. Now what happens at location B is that the pendulum slips, right? So what is the force experienced by the pendulum? The forces experienced by the pendulum midway are essentially gravity and tension, right? So let's look at those forces. So at location B, the forces are, well, you have the gravitational force acting downwards, mg, and the tension which is acting upwards, T. Mg is the gravitational force, which is a conservative force field, and T is a contact force, so it's not conservative. Now, if I apply the Newton's second law, which is if I apply the Newton's second law for radial motion, because essentially the pendulum is executing circular motion. So if we analyze circular motion, we need to apply the Newton's second law in polar coordinates. So if I apply the Newton's second law in polar coordinates, I'll have two terms for forces, one along the radial direction, one along the transverse direction. So if I represent the forces along the radial direction, I can simply write this as MAR, where AR is equal to R double dot minus R theta dot square. This is essentially the Newton's second law in polar coordinates. Okay, this is the form of the Newton's second law in polar coordinates. Now, what is r double dot? It's a change in the radius. Now, what is the radius here? R is nothing but equal to L, which is a constant. So, the second order derivative of a constant term is 0. So, this comes out to be minus m, r is again L. Now, theta dot is the angular velocity. So, theta dot is nothing but omega, but we know that v, which is the velocity along the transverse direction or the speed along the transverse direction, is equal to omega r or omega L. So, for pure circular motion, which is what's happening right here, this gives you an idea about the speed along the transverse direction and omega, which being the angular velocity. So, this can be written as ml v square upon L square. So, this is going to be m v square upon L. So, what are the forces along the radial direction? This gives us this particular equation. Now, what are the forces along the radial direction? Well, outward radial direction I have mg, and inward radial direction I have minus t, because it's acting, the radial direction is essentially this direction, right? Outward radial direction. So, this is equal to minus mv square upon L, and from here I get tension T is equal to mg plus mv square upon L. This is basically a relationship for the tension in the string of the simple pendulum midway in its motion, the moment when the slip happens. So, what have we done till now? We have figured out what is the nature of the speed at the point where the slip happens, and what is the tension in the string at the point where the slip happens. The reason being, I want to replace this v square upon L from point number 1. So, if I can replace this from here to here, if I replace 1 in point number 2, this expression is going to simplify and give me a new tension, which is mg plus m v square upon L is equal to 2g1 minus cos theta. If I simplify this further, this is going to give me, so if I write this here, this simply ends up becoming T is equal to mg 3 minus 2 cos theta. Alright. So, this is what I have finally obtained. This is a tension on the string at location B when the slip happens, when the bob goes from B to C. Now, why do I need the tension? I need the tension because the method that I am going to employ to actually solve this problem involves work done by a non-conservative force. You see, it's easy to calculate the work done from conservative forces. You look at either the potential energy difference or the kinetic energy differences, right? But here, because the tension is involved and tension is a non-conservative force, it's a contact force. So, I'm going to employ a theorem here. So, work done by a non-conservative force as it goes from B to C, right? So, the pendulum goes from B to C. B to C is basically the path that is created because of the slip of the pendulum. So, what is the amount of work done as the pendulum goes from B to C in a very short interval of time is equal to, because the forces that are involved are not conservative, the tension is not a conservative force. So, because of the tension, the forces that are involved is equal to EB minus EC. So, where E is the total energy, okay. So, E is the total energy of the system at point B and EC is the total energy of the system at point C. So, the difference in the energies correspond to the work done by the tension here, okay. So, this is the theorem that I am going to use. This should be EC minus EB, okay. Now, if you look at this term, what is the total amount of energy at location C? Well, it is the same as the total amount of energy at location D, right? Because during this motion from C to D, only conservative forces are involved, therefore energy is conserved. So, this I can write as E D minus, what is the total amount of energy at location B? Well, this is the same as the total amount of energy at location A, right? Because in this path, the total amount of energy is conserved. So, this is equal to E A. So, what happens is that during this motion from A to B, energy is conserved. During this motion from C to D, mechanical energy is conserved. Work is only done due to the non-conservative forces when the slipping happens. Therefore, I am finding the work done due to the tension as the difference in the energy between locations D and A. So, we have the tension here T, And what is the shift or what is the displacement from B to C? That is del. So if I write this, it can be written as W work done, which is equal to minus tension. Tension is acting upwards against the radial direction. So T dot del, okay, is equal to the total amount of energy at point D. What is the total amount of energy at point D? That is equal to the kinetic plus the potential energies, right? But the object is at rest. When it reaches the other end, the object is at rest. So that is KE D plus KE, or rather V D. KED is equal to 0. Similarly, minus KEA minus VA, where the object was initially at rest when it was at A, is equal to 0. So this essentially becomes minus T del is equal to VD minus VA, which is the difference in the potential energies between locations D and A. Now I am going to apply tension that I have earlier derived in this particular equation. So let me write what the tension is that I have obtained. Tension I have obtained as mg 3 minus 2 cos theta. So I am going to keep this here and I am going to erase the left hand side so that I can do the further calculations. So let's start with this equation then, okay. So we have minus T del is equal to Vd minus Va. What is Vd? It is a potential energy at location D minus potential energy at location A. So we need to calculate the potential energy based on some common reference. The reference can be anything as long as we make a common reference. So it's better to choose the reference of the ceiling, right? So if I choose the reference of the ceiling, then I can calculate the potential energy for both A and D positions. So for Vd, mg, this height, what is this height? L plus del cos theta dash. So this is equal to Vd is mg L plus del cos theta dash. So this is the angle by which it is displaced on the other end, minus Va, which is equal to minus minus plus mg. This is supposed to be minus, okay. So if I take this as 0 reference, so I will calculate this as negative. So this is minus and this is minus and minus becomes plus mg L cos theta. Alright, so let us substitute the tension that we have obtained here. So this is the tension that we just obtained. So tension is equal to minus mg 3 minus 2 cos theta is equal to minus mg L plus del cos theta dash plus mgl cos theta. The mg gets cancelled out and finally we are left with 3 minus 2 cos theta is equal to L plus del cos theta dash minus L cos theta. There was a del term here also, right? There was a del term here that I forgot to write. So this is the del. So there must be a del term here and there must be a del term here. Alright, so now this is the relationship essentially between theta, theta dash and del, which is the slippage length of the pendulum wire. So I'm basically interested in figuring out what is the relationship between theta and theta dash. So if we start the pendulum with an angle theta, how far would it extend on the other end, theta dash, if the length has changed midway? So for that, I'm going to make a couple of approximations because otherwise the calculations are very, very complicated. The approximation I'm going to make is small angle approximation. So I'm going to assume that we are dealing with small angles. Theta and theta dash both are small angles. So if we make small angle approximations, then cos theta is approximately equal to 1 minus theta square upon 2 and cos theta dash is approximately equal to 1 minus theta dash square upon 2. If I substitute these expressions here, then this is simply going to be equal to del 3 minus 2 1 minus theta square upon 2 is equal to L plus del 1 minus theta dash square upon 2 minus L 1 minus theta square upon 2. Essentially, it's a mathematical problem where I'll have to simplify all the terms to come up with the final answer. So let's do that. So what do we get here? So this is just del 3 minus 2 plus theta square is equal to, if I take L out, this becomes 1 plus del upon L 1 minus theta dash square upon 2 minus L 1 minus theta square upon 2. So 3 minus 2 is 1. So this simply becomes del 1 plus theta square is equal to, again if I take L to the left hand side, this will become del upon capital L. So I should get 1 plus theta upon L 1 minus theta square upon 2 minus L 1 minus theta square upon 2. This is theta dash square, by the way. Okay, so this simplifies to del upon L plus del upon L theta square is equal to 1 plus del upon L plus 1 plus del upon L times minus theta dash square upon 2 minus L plus. So L I have already taken to the left hand side, so therefore I should have removed it here. So this does not require L. So this essentially becomes minus 1 plus theta square upon 2. So del upon L gets cancelled, 1 minus 1 gets cancelled. So if I take this term to the left hand side and the rest to the right hand side, this simply becomes 1 plus del upon L theta dash square upon 2 is equal to theta square upon 2 minus del upon L theta square, which is nothing but, if I take theta square common, this is, or rather if I take half theta square common, this is 1 minus 2 del upon L, where half and half gets cancelled, and finally theta dash square comes out to be 1 plus del upon L to the right. So it becomes minus 1, and then we have here 1 minus 2 del upon L theta square. Alright, so it seems like a lengthy calculation. This is because there are so many terms involved. We can further simplify it by using binomial expansion, right? This is 1 plus del upon L. Now I also have to make the assumption that del upon L is small enough, okay? Because if I make the binomial expansion, what I want to do is theta dash square is equal to 1 upon del upon L, and then there are going to be higher order terms, right? Powers of 2, 3, 4, etc. But if del upon L is small, then we can say that, for example, del square upon L square is very, very small, so that we can ignore it and higher order terms can be ignored. So if we do that, it will only have 1 plus del upon L. The remaining terms we will ignore, neglect, because this itself is small. So this comes out to be 1 minus 2 del upon L theta square. So let me rub the right hand side to create some space. So finally, I need to now simplify this expression, okay? So let's take this expression here and try to simplify it here. So del dash, or rather theta dash square is equal to 1 plus del upon L into 1 minus 2 del upon L. So this is nothing but 1 plus del upon L minus 2 del upon L minus 2 del square upon L square. Again, this I am going to approximate to 0 because del upon L is small, so del square upon L square is going to be even smaller. So this is theta square here. So theta dash square is equal to, this ends up becoming 1 minus del upon L and theta square. Now this is a relationship between theta dash square and theta square. If I want to find out what is theta dash, this is going to be equal to 1 minus theta upon L to the power half theta to the power 1. So again, I am going to use a binomial expansion here. Again, I will get multiple terms. So the first two terms I am going to retain, rest I am going to ignore because they are very, very small. So this is going to be 1 minus theta upon 2L theta. Just wait a minute. I think I made a small mistake here, because when I was expanding this to the power of minus 1, I should have put a negative sign here, okay? Otherwise the answer will come out to be different. Because I am expanding to the power minus 1, it is a binomial expansion, I am ignoring the higher order terms, there should be minus 1 here. So if there is a minus 1 here, there will be a minus 1 here, and then this is going to be equal to minus 3 del upon L. So minus 3 del upon L, so minus 3 del upon 2L. Alright, so essentially then we have found out the relationship between theta dash, which is the angle by which the pendulum will create a displacement at the very end on the right hand side, is equal to 1 minus 3 del upon 2L times theta, which is basically the initial angle. So this is not the same. So as you can see, because the pendulum's length changes during its motion, theta is not equal to theta dash. So initially if the pendulum started with a particular angle and the moment it slips, it will go on the right hand side, it will go to a different angle. In fact, theta dash is less than theta, alright. So L is the length of the pendulum initially, del is the change in the length the moment it slips. So theta dash is in fact less than theta, you see, theta dash is less than theta. So this gives us an idea about what happens if a pendulum slips midway during its motion, then what is the relationship between the initial angular displacement and the final angular displacement for both these two configurations. And we have obtained this by calculating the tension at the midpoint, by calculating the velocity at the midpoint, by using the work energy theorem for non-conservative forces. Because tension is involved, I use the work done by non-conservative forces, which is essentially the change in the total energy in the configuration. By using these multiple concepts, we have been able to come up with this particular answer. There can be other approaches also which leads to the same answer. For example, you can also apply conservation of angular momentum, suppose. So because with respect to this point, the entire system's angular momentum will remain conserved. So you can use that approach also, but you will end up coming up with the same answer here. So this is the answer to the question, what happens if the pendulum slips midway during its motion, and how the initial and the final displacements are related to one another. So that is all for today. Thank you so much. I'll see you next time. Bye-bye.